We're looking at infrared spectroscopy. It's concerned about functional groups and ultimately bonds. Okay, that's our big goal. So when you hear infrared spectroscopy, it's bonds. So if I ask you, what does IR spectroscopy show you? You're going to tell me bonds. Okay? And in particular, a single bond. Okay? It's not really giving you functional group information. Once you've identified a bunch of bonds, you could start to put those bonds together and make functional groups. Okay? More information can be found in your textbook, your Making Connections book as well, and then I've also posted a supplemental guide which might be a little bit more relevant to you because that shows the actual spectra obtained from your instruments here. Okay? So make reference to those. That'll help you go through and do IR spectroscopy. So one of the things that we learn about or through using IR spectroscopy is functional groups. So we got to get an idea of what functional groups are, why they're important, all that kind of fun stuff. Ultimately, when it comes to functional groups, the biggest difference or the biggest deal for us is that it changes our chemical reactivity. Okay? If we have different chemical reactivity, that changes everything that we could do. Okay? So if we wanted to do a particular reaction or change our structure, we need to know what those functional groups are, how they interact with other things. Okay? So that's your biggest concern about functional groups. Other things that will bug you during the semester, in lecture you get tested on nomenclature, being able to name individual compounds. Well, because we have a functional group with different chemical reactivity, what do we do with its name? We also name it something different. Okay? So you need to be familiar with both the nomenclature, how the names change with each of the functional groups, and then also how you can classify and group them all out. Okay? And how they would individually react. Everything starts with pretty much the baseline of the carbon-hydrogen bond. Okay? That's where all reactivity is sourced from. We kind of go back to that as our general comparison. So what we're looking at is, say, just our carbon-hydrogen. What we can do is start to change that structure. Okay, if we move to an alkene, okay, in my opinion, not the easiest transition to make, but we can do it. Okay, what changes, say if we put a hydrogen up here, what changes about the bond between the carbon and the hydrogen? Does anything change?
Hybridization.
The hybridization of the carbon changes. Hybridization is looking at what?
Domain.
What domain? Right idea. The electron domains. Okay, so if we look at a bond, we're looking at the electron domains between those two atoms. If we change the hybridization, what are we doing to that electron domain? We're also changing it, which means the bond changes. Okay, well, if the bond energy changes, what does that mean about the reactivity? The reactivity also changes. Okay, so as we go through and alter the hybridization of our atoms, we change the energy of that bond. If the energy changes enough, we decide to classify it with a different name and a different reactivity. So we can now refer to that different functional group. Okay, so that's where we get our alkenes, alkynes, and our aromatic compounds. Okay. In my opinion, it's easier to compare, say in this case. So if we go back to our carbon-hydrogen, okay, and we look at our carbon-hydrogen bond, and we're now going to compare it to, say, an alkyl halide. Okay, what's the difference? In an alkyl halide, we've got a carbon still bound to a halogen. So in this case, I'm putting up a chlorine. Well, what changed as we went from an alkane to an alkyl chloride? The hydrogen is now chlorine. What's the difference between hydrogen and chlorine? Electronegativity and number of electrons, or ultimately size. Hybridization's in effect too. But, okay? So when you're looking for reactivity, those are our two primary things to look for: size and electronegativity. In this case, we would focus more on the electronegativity. How is that going to affect the reactivity of this molecule? Well, let's look at the electrons in the carbon-hydrogen bond. How can we classify that bond? What type of a bond is it? There's a bunch of different answers that the morning tossed out. What's that? Polar covalent between carbon and hydrogen?
No,
It's just covalent. We'll come back to that question in a second. Between carbon and hydrogen? Maybe I did. Between the carbon and hydrogen, we're looking at a covalent bond, which means equal sharing of electrons. So what partial charge builds on the carbon? None. Okay? So if we're now going to look at how that bond or that molecule interacts with another molecule, would we expect there to be any attractive force between them? Remember, your carbon's neutral. It's already happy. It's already in its stable state. Would we expect it to interact with another neutral molecule? There's no driving force. There's nothing to stabilize. It's already stable. So what does that mean about the attraction of that force between them? Do we expect strong or weak?
Weak.
We would expect a very weak attractive force. That's where we get our LDF forces, our London dispersions. What happens when we move to, say, a carbon-chlorine bond now? What type of bond was that? Polar covalent. Okay. What does that mean about the partial charge building on the carbon? Starts to become partially positive. Why partially positive? Because the chlorine's more electronegative and our chlorine starts to build a partial negative. If we're now going to look at how that atom or that molecule can interact with another molecule, would we expect a stronger interaction? Yeah. Why? We're trying to neutralize those partial charges. Okay? So that can explain the reactivity that we might see within the alkyl chlorides. Okay? If we now move to, say, an alcohol, what's the difference between our carbon-hydrogen versus an alcohol? Now we've got an oxygen in there. Okay? That oxygen is electronegative. How does that affect the atoms around it? Okay? So we're looking at minute changes, and each of those changes ultimately changes the structure, changes the functionality, changes our name. So what we want to do is to be able to classify each of these functional groups according to their particular names so we can make reference to them easily. Okay? One thing that you'll see, particularly with the CZ type bonds, is you might hear them referenced as primary, secondary, or tertiary. In theory, you've already heard this in lecture. What does primary mean? First, that works. Give me a little bit more. I don't quite want R group. I weren't really looking for carbons in this case.
First in the chain?
Okay. It's not even that. It's just the number of carbons it's attached to. So if we take a look at our alcohol, this first alcohol here, so there's our OH making an alcohol. What we'll do is classify the carbon that alcohol is attached to. And what we'll do is look at the groups attached to it. Hydrogen is so unimportant that we typically imply it, so we'll ignore the hydrogens. We'll look at what's left. We left this as an R group, which isn't particularly nice. We're looking for carbons. If that's a carbon, we've got one carbon attached to it. So we could call it a one-carbon alcohol. That's kind of a wishy-washy name, so let's come up with a better one. Let's call it primary. What happens if we look at our group? We'll ignore our hydrogen again, but now we've got two of them. What comes after one? Two, or second, or secondary. Okay? And then you've got tertiary. You're attaching three groups. The amines are similarly classified. They're slightly different as far as we go through with those, because we'll classify them based on the groups attached to the nitrogen itself. Okay? So being familiar with that primary, secondary, tertiary classification can help you out. If we go through and now add more bonds to our structures, we start making double bonds, making pi bonds. We're changing the chemistry just like we did with the alkene, but now we're bringing in our other atoms into this. Okay? So if we look at our first case, we've got a carbon-oxygen double bond. And we've got a carbon-oxygen double bond here. Okay? So what we've generated is a new functional group. We've got a carbonyl. Okay? Well, what happens if that carbonyl, that carbon is bound to a hydrogen? Okay, so if we look at the aldehyde, our chemistry changes because we're looking at a hydrogen versus an R group. And that R group in this case is being any carbon group. Our chemistry is now changed, so what do we have to do? New name. So we get aldehydes and ketones. Okay? What happens in the case of the carboxylic acid? We still have that carbonyl, but now what's that group become on the side? We've got an alcohol. We've got an alcohol next to a carbonyl. So we've taken two functional groups and we've put them near each other. Would we expect those functional groups to interact with each other? Probably. which means what ends up happening, we've generated now a new type of functional group. And in that case, we've combined, okay, two smaller functional groups near each other. It changes, again, our chemistry enough that we change our overall name. Okay, and that's where we get our carboxylic acid. Okay? So pretty much any time you take a simple functional group, any of the sigma bond ones, and you put it near another functional group, you end up generating a new functional group. So we can get a fairly large amount of these. You're only responsible for some of them. Okay? Most of that's happening in lecture. So we said the chemistry changes, the reactivity changes. But it would be kind of an unfortunate or a crappy way to identify these functional groups is if the only way we could find out is if we reacted them. So we took our compound, we threw it in a mixture and said, what happened? Did it react? Oh, that means it was this one. Okay? That's a lot of work to go through and do. Okay? You'd have to run the reaction, isolate your product, identify the product, all that fun stuff. So we want a simpler method. One way that's not destructive, is not going to change the structure. And so what we're going to move to is spectroscopy. Okay? So we can break down the term spectroscopy. Spectra stands for, as a guess, it's color-coded on the slide. Energy. Okay? So we're ultimately looking at one option is light. Light is just a form of electromagnetic energy or radiation. Okay? The O, I didn't really have anything creative to come up with, so we just left it as O. What does scopy mean? Observation. It's what you're looking at. Okay? So spectroscopy is just a way of taking energy and using that to make an observation. Okay? So when we're looking at IR spectroscopy, we're taking IR energy and we're using that to observe our compound. Okay? So depending on the type of energy we use, we can get different effects on our structure. You guys have already used the UV spectroscopy. You did that with your colorimeters or your ultra UV vis absorption equipment. Okay? And in that, you saw electronic transitions. You took an electron from a ground state, you moved it to an excited state. Okay? Excuse me. What we're going to look at now is IR light. Which one's higher in energy, IR or UV? UV, how do you know that? Because the graph shows it. That's a good first answer. Let's say you don't have the graph. How do you know it's higher frequency? How do you know anything about its wavelength? From the graph. So that's going back to another graph. Can't go to a graph. When you walk outside your random Joe Schmo on the street, do you know anything about the frequency, energy, or frequency or wavelengths? Probably not. Do you know something about energy? Kind of, sort of. When you walk outside, okay, you're always told, particularly during the summer, that you need to put on a protective coating. What's that protective coating against? Ultraviolet light. Do you ever hear anybody tell you need to protect yourself against the IR light? Okay, why not? It's lower in energy. Okay, so you've got a quick, easy way to remember the difference between the two. Okay, well, we said ultraviolet light was higher in energy and actually caused an electron to physically move. Wow, big deal. How big is an electron? Yeah, pretty small. Okay, so it jumped energy. So if we move to IR light that's even lower in energy, that can't make any of our atoms or nuclei move. We aren't going to see nuclear transitions. We're not going to see electronic transitions. So what do we end up doing? Okay. What is IR light? Ultimately heat. Okay. So what we're going to end up doing is heating our sample in a very controlled fashion. Why is that relevant? What happens when we heat things? They start to vibrate. And what we're looking at for our molecular transition when it comes to IR spectroscopy is molecular vibrations. Okay? And in very, very particular cases, what we're looking at is the bond vibration. Okay? So if we look at an individual bond, that's going to have a characteristic energy associated with it, and that bond vibration is what we're going to detect when we look at IR spectroscopy. So we need to understand what a bond is. So if we took this case, we looked at an atom here, so we'll take atom A, draw a bond, and make atom B. When we draw that, we typically draw the bonds as the same length, right? In general, pretty much the same thing. We envision them as kind of static things. But are they static? No. I can take atom A and atom B and I can pull them away from each other until eventually what happens? There's no bond. Or I could bring two atoms near each other to the point where we start to form a bond. So it's a gradient. Okay, what we're looking at is pretty much a spring. If we pull those atoms further apart, we start to build charges. Charges are bad. What happens? They start to be attracted towards each other. So what we're looking at is that spring energy. Okay, all bonds have a characteristic vibration associated with them. Okay, what happens though if I change atom B? I don't like atom B. Let's look at, say, let's take a look at atom C. Would I expect my bond to vibrate differently? Why would my bond vibrate differently now? Because C is bigger. We've changed one of the ends of that spring. Okay, so if we took two 5-pound weights and attached it with a spring in the middle and we let it release, it would oscillate. What if we change one of those weights to a 50-pound weight? It's going to oscillate differently, right? There's a different energy associated or stored within that bond. That different energy is what we're going to detect and try and control and manipulate when we deal with IR spectroscopy. Okay? So when we look at individual molecules, we're going to look at different types of vibrations, and the vibrations that we're primarily concerned about are your stretching vibrations. Okay? There are other types of vibrations that you could get. Those are typically classified as your bending vibrations. We aren't as concerned about those. If you really want to dig into it, you can look in your textbook. It'll tell you more information about the bending vibrations. The stretching ones, almost all of the stretching ones, we require you to have memorized. Okay? So you should become familiar with those pretty much right away. Every bond has a characteristic energy, which we just talked about. We're going to convert that into a frequency. That frequency can be matched in the IR spectrum. Okay? So the instrument itself, we're looking at IR light. So we've got a glowing source that's going to release IR energy. That energy is going to get shuttled off through a reference cell and through your sample. Okay? And what we're going to end up doing is then looking at the energy that passes through and makes it to our detector. So what we're going to do is just scan the frequency of the IR spectrum and see what happens. And what we're going to monitor based on is the percent transmittance. How much light makes it through the sample. Okay, let's assume there's no sample there. How much light would make it through? A lot. Or we could convert it into a percent. We would expect 100% transmittance. Okay? What happens if we put a compound in there? Well, as we start to scan our frequency or our energies, maybe the molecule doesn't absorb. So we don't see a change in our absorption or percent transmittance. All the light continues to pass through until eventually what happens? Whoop, there's a bond. That bond happens to absorb that energy, and we end up seeing our spectra. And that's where our peaks come from. Okay? So each of those peaks ends up being the spectra that represents an individual bond. It's the nature of that bond. Okay? So when you're looking at these, what you're trying to do is to control those or to see what's happening and use that information to interpret some information about your structure. Okay? The instruments themselves, you guys should all be familiar with these now. There's two types that we've got in our labs. The second floor, unfortunately, has the, cover up the audio, the crappy old ones. And the third floor has the nicer new ones. Okay? When you go through and use those, I've zoomed in on the part that you're concerned about in each case. They're set up very, very similarly. You would put your sample right, come on, draw, right in the center of that little black dot. Okay, if it's a liquid, you can put everything just directly on there, and then you just go ahead and click scan, and you're all happy. If it's a solid, what you're going to have to do is swing the arm on the third floor over the top, and then use the anvil top and crank down until you feel some resistance. That resistance is forcing your solid against the the detector so that it can actually see the sample. If we're on the second floor, we got a similar setup except it's on the side. You crank your black little knob until that stops moving. Okay? It's going to compress your sample down so that, again, the equipment can see it. You've got a general procedure there. You should all be familiar with that. Your TA in theory taught you all that information. Okay? So we'll just go ahead and move on from there, unless you guys have questions about that. Good, I like that. So we'll go ahead and move on. As far as interpreting the spectra goes, every bond has a characteristic energy associated with it. Okay? So all we're going to have to do, or all we expect you to do, is to go back and reference a library of all of these types of bonds. Okay? With the previous labs, we had you compare the full spectrum, because the spectrum should be identical. Now you have to compare signals, and you're only looking for independent signals. Okay? Again, you're going to have to rely on a library. That library can be formatted in different fashions. You've got one at the very last page of your group activity. It's also in your textbook, and it's also everywhere you can look on IR spectroscopy. They're going to have some version of this. Okay? Depending on how advanced material that you're pulling at, you might get a simple version or a more complex one. Okay? All you're doing is matching game. What you're going to look at is compare the individual signals between your sample and your standard and just try and match them up. There's three primary ways you can compare them. The wave number, which is our frequency, it's the energy of light that it absorbed. Our intensity, how much of the light did it absorb? And then also the shape. So you compare based on those three characteristics, and you should be able to identify your compounds. Okay? You'll notice that most tables don't give you sample spectra to look at. The posting that I put up onto Blackboard gives you sample spectra. So when I say an alcohol stretch, I give you an example of an alcohol stretch from the equipment that you use in lab. So it's the exact same data. Okay? So if we look at a couple spectra, you've already seen these before. There's a lot of signal going on in this. We want to kind of simplify that. So depending on your professor, you may actually see on exams a line get drawn right about 1400. Which side do you want to analyze? The one with a lot of peaks or the one with a few peaks? Few sounds easier, so let's do the lot of peaks one. And to analyze that one, what are we going to do? We'll call that the fingerprint region, and our analysis is pretty much summed up like this. We're going to ignore it. Okay? And we're going to focus all of our attention where we've got just a few peaks. Okay? And what we're going to try and do is, again, identify those signals and compare them back to our standards, okay, our library of information. So in this case, I see a big, broad signal that shows up right about, what is that, 3,400, 3,300? So I would go back to my table and say what signal shows up at 3,400 that's broad and fairly intense. And I would decide, oh, that's an OH. Okay? I could then go through and say I've got another signal here, or series of signals. What shows up just less than 3,000 gives me a couple different peaks there. Go back to my table, and I'd find that it's CH stretches. But when I look at the table, it adds some extra information. It doesn't say just CH. What else does it tell me? It tells me alkanes or sp3 hybridization. If we look at the structure that we're dealing with here, remember IR shows you bonds. What bonds are in cyclohexanol? List them off. What bonds do you have? C double bond C, is that what you said? Do you see a C double bond C in cyclohexanol?
Oh, whoops.
What else is there other than the C double bond C that's not? We've got the hydroxyl, so what you're referring to is the OH bond. What else is there? We've got a carbon-oxygen bond. What else is there? We've got carbon-carbon bonds. What else is there? Carbon-hydrogen. Let's be more specific on that carbon-hydrogen. It's sp3 because the carbon is sp3 hybridized. Okay? We would expect and predict that we could find all of those bonds within our spectra. Some of them fall into the fingerprint region, which is why we don't analyze them. Okay? So, this is the IR chart given to you on the back of your thing. You should memorize everything that shows up on this chart. Okay? You might be supplied it on an exam, but in most cases you're going to be asked to have it memorized. The one that I would not waste any time memorizing would be the carbon-nitrogen triple bond. Any ideas why that's useless to memorize? It's the same as the carbon-carbon triple bond. So why bother to memorize something that's just repetition? Okay? The triple bonds are nice because they're the only thing that show up in that range, so I also usually don't memorize them because if I see anything that looks odd in that range, I know it's a triple bond. Okay? So we'll go through a couple quick examples here. Skipping to a particular one. I think it's unknown D. Yep. So what we would go through to do to analyze unknown D is find those signals. The first thing that we could do, okay, is put down our 1400 line so that we know that we shouldn't be starting our analysis in that range. And we try and find signals elsewhere to see what else we could find. Okay? This case, we happen to have some things labeled for us. I see two peaks, 3400 and 3300. I would classify those as fairly broad. Why would I say broad? Okay, because it's not sharp. What would sharp look like? Okay, if you look towards the ones on the right, those are sharp signals. So we've got a broad, relatively broad signal, multiple peaks though in that range. So we'd go back to our library and say what things show up in that range. Okay, we could have the CO, but that's really broad and really strong, okay, which isn't going to help us out. And then we get NH, broad with spikes. So it's not just a single peak, but potentially multiple peaks. And we could also have the CHSP, which we're saying shows up very, very sharp at 3300. Okay. How would you know to distinguish this series of peaks from an alcohol versus an amine? Practice. You would have looked at the individual spectra. You'd recognize that an alcohol should show up as a nice broad signal. This is not a nice broad signal. This is multiple peaks. So we'd be looking at an NH peak. These peaks at 3100. We'd go back to our library and say what shows up in our library at that range. We'd find carbon-hydrogen, sp2s. Okay? We could go all the way down to about 1600. 1600 happens to be characteristic for carbon-carbon double bonds. How do I know all this information? Because I've been doing it for a ridiculously long amount of time, so I've got them all memorized. Okay? So when you work through with these, make sure you're looking at different tables. The next piece of information I'm going to point out, which is going to be particularly relevant for your assignment, not only is this just an NH, that is a primary NH, a primary amine. How do I know that? There's two peaks. How do I know two peaks represents two hydrogens? Only applies to amines. Okay, IR typically tells you nothing about the numbers of bonds. It tells you just that it's there. Why do we see two peaks? Because we get two different types of stretchings that can come out of that signal. And what we end up doing, how would we find out that information? We look at page, sorry, I must steal this from you. You look at page 3, next to amines, it says NH2 equals two peaks. And NH2 is a primary amine. Okay, that's the only place it's shown in this handout. If it was a secondary amine, you'd only see one peak. Okay? So we're going to let you guys work through this. If you've got questions, raise your hand and ask. Most of it is just trying to identify the difference between these. Find the differences, find the similarities, and start to play your matching game.